Hello everyone, Daniele here. In this video I want to implement sequence of numbers that has been musified repeatedly by Danish composer Per Nørgård. This has been brought to my attention by Gabriel Bolaños, whom I want to thank. We will base our analysis on a paper, like we did for the Risse video. The paper is this one, Notes and Note Pairs in Nørgård's Infinity Series by Eugen Gary Au, Christopher Drexler Lemire, and Jeffrey Shallett. We can go straight to the point. The sequence is defined recursively, as you can see here, and it's a sequence of numbers that starts with 0, and then if n is even, is defined in terms of the element at position n divided by 2, with the opposite sign. While if n is odd, is defined by via the element n minus 1 divided by 2 added 1. This is a recursive formula, which means that if I start from 0, I can get all the other numbers from there, like number 1 would be odd, and I can do 1 minus 1 is 0, divided by 2 is 0, so I just take 0 as 0 and add 1, which as 0 is 0, we know it because it's the basis of our recursion. And so we get 1 as as a second element. So let's say element of position 1 at n equal 1. At n equal 2, n equal 2 is even, so we get the opposite of 2 divided by 2 is 1. So the opposite of S1 was 1, so S2 will be minus 1, and so on and so forth. The actual sequence can be seen here: 0, 1, minus 1, 2, 1, 0, minus 2, 3, 1, 2, 0, and so on. It has some nice properties. For instance, you can see that it does not go up and down very fast, so it stays kind of in a limited range for a long time, and it's kind of random or random-like in the middle. It's not really random, but it looks like it's sort of random, but with patterns that actually repeat. You can spot some of them, perhaps. One of these patterns is about self-similarity. You can perhaps see that by taking every second element of the sequence, we get the same sequence inverted. And there are many other ways to get the same sequence inside the sequence. Perhaps you can have a go and find some, or you can read the article to know more. It's an interesting sequence. That's the bottom line. This sequence can be thought as intervals from a given note. So 0 is this G at the beginning. Then 1 is 1 semitone higher. Minus 1 is 1 semitone lower. And so if you start from this G and apply the sequence, you get a sequence of note. You get a musification of the sequence. And this is, for instance, how Nørgård used it in his voyage into the golden screen. This video will be in 3 parts. In the first part, we will just implement the sequence as proposed in Bell. So we learn about recursion in Bell. In the second part, we will extend, we will generalize the sequence so that we can start with 2 arbitrary notes instead of 1. So here we start with 1 note, which we call 0, let's say, then we can shift it wherever we want. But if we start from 0, then the sequence is all determined from there. There is a generalization of this sequence that can work when you start with 2 arbitrary notes. And we will see that. We will refer to an online article, the link will be in the description, by Jørgen Mortensen, Construction by Programming, where at the very end he gives this generalization formula for the Nørgård sequence. And finally, in the third part, we will apply a lemma in this article, lemma 3.1, which actually gives us the sequence directly without any recursion. And as an exercise just for us, we will do that in plain Bach, not in Bell, without using Bell or Bach-eval at all. So let's start with number 1. Let's define a variable called Pn in bach.eval. This variable will actually contain the function s, as represented in this article. So we'll not call the function s, but we will call it pn for Per Nørgård. Just a reminder, you should not call your own global variables with an initial lowercase letter. That's not really advised. It will work probably, but lowercase letters for global variables will be reserved in the future for additional functions that will be added to the Bell environment, which means that if you want to be safe for the future, you should always call your global variables with a capital letter first. So pn is okay, pn not so much. Let's go with the capitalized version. And this variable will contain a function. And to define a function, we need to have a couple of parentheses and an arrow, which actually assigns, given some parameters, the value of the function. Our parameters is just one. It's called n. So let's call it $n to be on the safe side. And then the value of the function depends on the n we have chosen. So if n is 0, the value of the function is 0. If n is even, the value of the function is this one. And if n is odd, the value of the function is this one. So let's do the 3 cases by using the keyword if. I'll put a level of parentheses just to be safe. If n equal 0, then let's return 0. Else, otherwise, and then we can chain the ifs. So else, if, how do we test if n is even? Well, if n mod 2 equals 0, then n is even. And in this case, what do we give? Then, well, in this case, we want to apply the same function, so pn, but with an opposite sign, and on the argument $n divided by 2. We are very sure that in this case, this division is an integer. It's not going to give us a rational number. If we want to be on the super safe side, there's no need in this case, but we could do this. This is the integer division. This is potentially a rational number. It's not, because $n is even. So let's stay with this. Else, in this case, we are sure that $n is odd. Well, in this case, we have to do pn of $n minus 1 divided by 2 plus 1. Okay, so I will close the parenthesis and add the attribute at auto1, which means that the code will be executed straight away when the object is created. So when I do that, now Bach eval has defined a global function named pn, which I can use anywhere I want. In particular, I can create a bach.roll and feel the sense, where are they? Here, with a bach.eval. Say we can start from the G5. Remember, in Bach, the middle octave is 5. And then we can collect, say, 100 terms of the sequence. How do we do that? Well, let's take a parenthesis, for E in the range from 1 to 100, collect Pn of $E. These are bound to be elements of this sequence, so 0, 1, minus 1, 2, and so on, which means that they are going to be multiplied by 100 if we want the midicents, as we do in Bach. G5 we can use equivalently 6,700 if you prefer. That's going to be the same because we are going to add it to a numeric value. This is going to yield the midicent number of our sequence, but we need to put some brackets. One bracket for the voice, that's for sure, and potentially one bracket for each chord, but we are allowed to ignore that. So let's stick with this and see if it works. So we just put a bang here and here, and here we go. We are missing the very first one because we have started from 1 instead of 0, while our sequence starts from 0. If we do that, you can see that we have actually the sequence that the article provided. That's exactly the same thing, except that there's a F sharp in the key signature here. We can do some cosmetic adjustments like hiding the durations, but it doesn't really matter. What matters is that this is how this sequence can be simply constructed. As you have seen, we have relied on calling the Pn function while defining the Pn function. This is called recursion, and it worked because at some point it stops. And when does it stop? Well, it stops when it reaches 0. So every number will be divided by 2 if even, or subtracted 1 and then divided by 2 if odd. At some point it will get to in any case, at some point it will get to 1. And once you're in 1, well, 1 minus 1 divided by 2 is going to be 0, so we'll get to 0. So we will fall back after a certain number of calls into the 0 case. And the 0 case is simply 0. So we can actually use recursion because it's well defined in this case. Let's now take the generalization formula provided in the website I told you about. This formula actually computes the same function Pn with the name we used, but different from before. When you compute it on one number, the computation doesn't only fall back on the halving of the number, more or less, give or take 1, but also on the same number minus 2. And this is a crucial difference in terms of performance. You can think about how the previous example worked in terms of performance. If I have like a number 16, say, 16, in order to compute Pn of 16, we had to fall back on Pn of 8, then on Pn of 4, then on Pn of 2, then on Pn of 1, and then we get to 0. In some sense, how the number of steps is proportional to the logarithm of the number we had to compute. That's why the recursion was kind of fast. In this case, this is no longer true. If we have to compute Pn of 16, well, we have to rely on Pn of 14 as well. And then Pn of 14 will rely on Pn of 12, and then on Pn of 10, and then on Pn of 8, and so on and so forth. So in general, the number of steps in the recursion will be not proportional to the logarithm, but proportional to the number itself, divided by 2, probably in this case. But in this case, it's in terms of complexity is O of n. We'll see this means that it's going to be slower, and there will be a much better way to do that. I'll point to that in a bit. But first of all, let's do it in the naive way. Well, first of all, we need to have starting values, which means values for the case of 0 and 1. We need 2 starting values in this case because we need to fall back on 2 different initial nodes. To do that, we can have, for instance, a bach.roll, which will contain, say, the starting nodes. And suppose we want to start with an F sharp and an A flat. Again, there's no need to show durations. In this case, we are only interested by the sequence. How do we define the starting points? Well, bach.eval, and say that A is actually what comes from here, flattened. The first element of what comes from here, flattened. Only this one will be in MIDI sense and not in MIDI, so we can divide it by 100. And since we want an integer division, we can use the double slash. We could be more tolerant and say we could round it instead of taking the floor, but it doesn't really matter in our case. We want to convert between MIDI sense and MIDI numbers, so we divide by 100. We suppose that everything is in the standard 12 tone equal temperament anyway. B will be L1.flat 2 divided by 100. And that's it. So here we define our constants A and B. These constants actually represent the first two notes in the sequence. We can use a loud bang dump sense if we want. Not low bang, of course, or loud mess. Why not? And also we may want to use a dump sense whenever we change the nodes in the interface. Here we go. So if we do that, we are sure that this has been updated. So the first notes are F sharp and A. To be sure, we can actually use bach.eval and do something like print A, print B. And if we send a bang, we should see the MIDI values corresponding to the two nodes. And indeed we do. Now that we have our starting points corresponding to n equals 0 A and n equals 1 B, we need to implement the recursion. And it's not very different from before. Let's create a function named the png in this case. So pn but generalized. And we need to associate, which takes as argument a number. We called it n. Let's call it n again. And if n equals 0, then it returns A. Else, if n equals 1, then it returns B. Else, again, there are two cases, and the one that you can see here in the formula. If n is even, then what do we do? Well, we have to return png of n minus 2 minus what? Png of n divided by 2 minus png of n divided by 2 minus 1. It's a bit of a mouthful, but this is the even case. In the even case, there's one parenthesis missing, and then we go. We have to take the value of n. N is 2 times I, okay? So n is 2 times I, n minus 2, this is n minus 2, this is n half, this is n half minus 1. And we do the same in the last case, which is odd n. We just say else. Else, we do png of, well, it's actually the same $n minus 2 plus, parenthesis, $n. In this case, this changes, png of $n minus 1 divided by 2. Okay, and this is I, if you think about it, because in this case, n is 2 i's plus 1, which means that I is n minus 1 divided by 2. Minus the same thing minus 1. So we copy paste just to be. Here we go. This parenthesis closes this one, this parenthesis closes that one, and we should close the if, the bigger if, and the function. So if I'm not wrong, this, let's add at auto 1 again. This defines the generalized formula. How do we apply it? Well, exactly in the same way as before. Bach.roll, bach.eval. We can do something like, in this case, we don't have to add any note as beginning because the two notes are already given. We just have to multiply by 100. And we collect for any variable you want. Let's call it j in 100. Well, let's keep it quiet for a bit. Let's do 20 and we will see why. We collect png of $j. As you can see, I can use the square brackets outside or inside, it really doesn't matter. They are the voice delimiters. So if I do that, I should expect to have generalized sequence. I do not, because I'm starting from 1 again. I should start from 0, because all these sequences are 0 based. Here we go. So this is a generalization of the Nørgård sequence. If I change this and I compute it again, you see that this changes accordingly. If I want to do 40, you will see it takes a little while. And if I want to do 60 or 50, well, even more. As you can see from the spinning wheel. Again, it is slow because this is not the smartest way to implement this sequence. If you think about it, in order to compute an element very far, we have to compute most of the elements before it, which means that actually we are repeating the same computation over and over again. For instance, to compute this one, we had to compute this one. But we did it twice, because when we compute this one, well, we could store it and use it once we need it for this one. So there's a much better way to compute this sequence, which is just keep track of what elements you had already computed. And don't use recursion directly, but actually use recursion with the table of elements that you had already computed beforehand. The first 2 elements are computed already. The third one relies on the 2, but they are already computed. The fourth one, we rely on the previous ones that are already computed, and so on and so forth. So we don't need to recompute things more than once. And that's the smart way of doing that. I will not do that in the video, but I will add in the patch attached to the video a solution which rely on a table that does not recompute things over and over again, which is much faster for this same issue. Let's get to the third part of the video. In this part, we'll actually do the same thing we did in the first part, only we will use a direct computation instead of the recursion formula. And we will do this via direct patching without using eval or any lines of code. Let's read first of all what this formula says. And it says you can compute the nth element, in this case n is called w, the wth element, provided that you have a binary representation of the number, so the number in base 2, and then you count how many ones are at the beginning, then how many zeros follow, and then how many ones, and then how many zeros. So it's actually a collection of segments of 1 zeros, 1 zeros, 1 zeros, and the length of the segments is B1, A1, B2, A2, B3, A3, and so on till Bn and An. Once we have this representation of our number n, we can actually compute the element of the sequence directly by summing up for any j from 1 to n this number here, which is -1 to an exponent times bj. The exponent is only there to tell us whether the sign of bj is positive or negative. If the exponent is even, it's going to be positive. If the exponent is odd, it's going to be negative. And the exponent is the sum from j to n of all the a with I. So why is it true? You can read it in the article. I will leave the link in the description. But for the time being, let's assume that it works, it does. And let's try to implement this. In this case, we want to take one number, which is w if you want, or n, as we called it previously. We want to convert it into base 2. We can use bach.convertbase from base 10 to base 2. And we have here in the right outlet the list of digits as a list. Let's see it in the Max console. If I input 7, you see I get 111. If I input 13, I get 1101. Those are the digits of the numbers in binary. If I output 9, say, it's 1001, 10, 1010, and so on. So those are the digits in binary. let's take this representation and let's break it down into patterns of ones and zero. So what we're interested in actually is the fact that if we have a sequence of ones and zeros, say this one, we want to know the length of each one of these subsequences, like how many ones are there, how many zeros are there, how many ones, then how many zeros, and so on. In this case, the length of these sequences would be 3, 4, 2, 3, 2, and 2. And those will be the numbers of B1 will be 3, if you can see that. A1 will be 4, this one. B2 will be 2, A2 will be 3, and so on. How do we do that? How do we know how many ones in a row and zeros in a row are there? Well, one of the simplest way of doing this is to split the sequence whenever the number changes. So let's add a level of parentheses in the sequence, whatever it will be, at the point where the number changes. If you want to split a sequence at some point, specific points, the way is usually to use bach.split. Bach.split has different modes and can be used in different ways. So what I suggest you do is to see in the help file. There's an example which does exactly what we want to do. Split at every change of number. And you can see in the Max window that it's exactly what it does. And it does it by using bach.change. You can use change perhaps, but bach.change is the easiest way of doing that. Whenever the number changes, we send a 1, meaning a new segment starts. And we use @keep2, which means, yeah, a new segment starts, but do not throw away the separator. So do not throw away this specific element. Let's do that. Let's do bach.split @keep2 with a bach.change. Okay. If the number changes, we send a 1. Otherwise, we don't send anything. Bach.split works in lambda mode. It expects to have a 1 at the point where we want to split the list. So the only thing we need to do, as in the help file, is perhaps use a trigger L null so that we are sure that the first element we give will not be the same as the last element we already gave. So it's a sort of initialization of bach.change. So we are sure that the first element that comes in it's novel, for sure. Let's check if this works. Let's have a bach.print split form. Now if we get, say, 10, you can see that 10 is easy, every element for itself. But if we say like 9, indeed the two middle ones are split together. And we can go higher, like 502. And you can see that all ones are together, then 0, then ones, then 0. Okay, now we have to take the length of all these elements. And to take the length of all these elements, the best way is to use bach.mapelan. Again, I'm not using bach.eval on purpose, because I wanted to show you how to do that in Patch. At max depth 1, because I only want to iterate on the root level. And for each one of the elements, we flat it and we take its length. So now, in addition to the split form, we have the split lengths. Split form length, let's say. And if I send 502, you can see that indeed 5121 are the lengths of the elements. Good. So this is B1, this is A1, this is B2, this is A2, and so on. We have to delace the elements. We have to divide the B's and the A's because they are interleaved right now. To de-interleave something, we can use bach.delays. We want to de-interleave 2 lists, so we use 2. Here we have the B's, and here we have the A's. We have to be careful about one thing, though. The list of A's may be shorter than the list of B's. How is this possible? Well, it is possible if the last number in the list, in the binary representation, is a 1. In this case, there's no trailing 0, and AN is actually 0. So in this case, we have to manually add the fact that if A is shorter than B, we have to add 1 0 at the end. We do that by using, for instance, bach.pad. Bach.pad pads a list until an output length is reached, and we can give a padding element. The output length, we will set it via inlet, so we can leave whatever we want, like 1. And the important thing is that the padded element is 0. We want to pad the list with 0. We want to pad the list that comes from here, but actually we want to pad it with what comes from with the length of B. So we need a little bit of a trigger logic. So first of all, we save into a bach.reg the list of A's. Then when B arrives, and only then, what we do is, first of all, we take the length of the list of B's, and this length will be the padded length. We can put it in the middle inlet, output length. Then we bang the A's and we pad them. At this point, we are sure that A's and B's have the same length, so we can print them. Let's say this is A's and this is B's if we want. Let's just check it before continuing. We should use bach.print instead of print, sorry. Here you go. And indeed, you can see that B's are 5 and 2, A's are 1 and 1. Let's take a case where the form does not end with 0, like in case of 9. 9 ends with a 1, and you can see that there's a padded 0 at the end of the A's. This is okay. Now A's and B's have the same length. It's easier now to iterate on them, because now we have to iterate on them. And how many iterations should we do? Well, all the iteration from 1 to n. You can see it. For every j between 1 and n, we need to sum this element. So for every j between 1 and n, we can actually do an iteration, like here. Let's iterate on the B's. Now here the B's comes one by one. And what we have to do is to sum them up. Only instead of summing them up crudely, we need to multiply them by this number. So the expression we are looking forward to is $I1 times -1 to the power of $I2, where $I2 is this sum here. So we have to sum it up. How do we do that? Let's close this and let's keep the formula handy at right. This is actually the sum of a sublist of A's. Precisely the sublist of elements that go from j to n. How do we take a sublist of elements from a list? One way of doing this is bach.nth. Nth, with a syntax, with a range syntax, is able to return the range of elements from the jth to the last one, because n is the last one. So we can do something like this. From whatever we will send into, it will be the jth, to the last one. This will give us the range of elements. Now we have to sum them all. Bach sum. And then we can plug it in as $I2, and this will be $I1. So this will be B times -1 to this power of sums. And then what do? We have to sum this all. So we collect them, for instance, and let's put a bang here, and let's move them so I can actually send the bang at the end at bach.collect. And once we have collect them, we just need to sum them. Again, bach.sum is our friend. It's not over, of course. We have to cable things properly here, but this is the logic behind the thing. You can use a bach.print to see it. We take the B's one by one, we multiply them by the appropriate factor, we collect them all, and we sum them. Now, what's the appropriate factor? Well, it's -1 to the power of those sum. How do we take the sum? Well, we take the range of elements of A's, so we need to have some sort of bach.regs. All the A's must be put here. And notice that the J, which identifies the elements that starts this sum, is actually the index of the element being iterated here. When we output B1, it's going to be 1. So we have A1 to AN. When it's to B2 is going to be 2, so A2 to AN and so forth. So we need to have it out an M, so that the first outlet is negative, the second one is max. And the integer will be $1 here. So we can take all the elements from the index that comes from here to the end, -1. And then we can bang the register, which contained the list of A's. This actually completes our implementation. Of course, we could do better. There's no need of computing -1 to this power. We just need to know whether this is odd or even. So we could do better than that. But this is a way of showing you that even with direct naive computation, applying this formula, we can actually get to the same result as we did in the case of recursion. Let's check it out just to be sure. So let's start with 0. We should get 0, right? We do. Indeed, the final answer is 0. Let's go with 1. Well, we get 1. Let's go with 2. We should get -1, if you remember. And indeed we do. And so on and so forth. That's all for today. It was a bit longer than usual, so thanks for bearing with me till now. And I hope you learned something, and stay tuned.